All right. Cool. Well, hi everyone. I'm Ryan Schwab again, instructor with Fly Life Paragliding. Um, Outside of being a paragliding instructor, I'm also a PhD student at Montana State University, getting a PhD in mechanical engineering with a research focus in flexible wing aerodynamics. So a lot of what I study is flapping wings. So I look at insects and small birds, mostly moths and bees. So to give you a little idea of what I'm doing, here in this little video clip, I've got a computational fluid dynamics model, which is solving for flow through this domain. And then you can see the plate that's in there that's starting to bend backwards. That's solved using a finite element model, which solves for deformation, stretching, bending, that kind of thing. And so a lot of what I work on is combining different types of models like these two to get holistic pictures of what's going on with flow around solid objects. So with that, and a lot of my kind of undergrad background, there were a lot of thermodynamics classes, and I've noticed that a lot of the material that I learned in those really applies, especially to the meteorology fundamentals. So without stalling any longer, I'll get the show on the road. So with meteorology, what we're talking about is weather and wind, and just kind of what's going on in the air. So it makes sense to start by talking a little bit about the air. The air is made up mostly of nitrogen, oxygen, and water. Now, each of these things has mass, has weight, which means that air as a whole has weight. And that weight, or in this case density, comes out to be about 0.076 pounds per cubic foot. And all that really means for us, and the reason that's important, is that anything with weight is affected by gravity. And so the reason that we have an atmosphere on Earth is because gravity is pulling that gaseous air down toward the Earth. That also means that as we move up in the atmosphere, we notice that the air starts to decrease in pressure and density. Now, the air that we fly in, you probably won't notice drastic changes in air density, but if you are launching at or if you're launching at 11,000 feet, you're going to notice that it takes a lot more speed to get moving, to get off the ground, than if you launch near sea level. And the reason for that is that air density. There's less mass, and so you have to move faster to make up for the change in momentum. So anyways, we'll start with some kind of basics here on how this air works. We'll start with density, and you'll see me label density like this kind of curvy P. That's a Greek symbol rho used for density. And density is affected by the temperature, the air pressure, the percent of water in the air, or the humidity, and the altitude. I'll be labeling altitudes as Z. Now with pressure, we can think about pressure as kind of squeezing and pulling of the air. We can think about density as how many particles of air are in a given amount of space. So if we had these two spaces here that were the same area or the same volume, on the left here, let's say we have these 5 little air particles, or on the right here, let's say we have a whole bunch of these air particles, and they take up the same amount of space, but they're packed in there tighter. So this would be considered a low density, while over here we'd be looking at a higher density. And now these are low and high relative to each other, not relative to any given kind of standard. So if we talk about low density, high density, or low pressure and high pressure, that means relative to what's around it. It's low or high. Cool. And then with that, we'll also look a little bit here at pressure and kind of how that works. So let's say we have 2 volumes. The volumes, let's say these are the same size and the same number of particles in there, so they have the same density. but you can actually think about kind of squeezing one or pulling on the other. What this looks like, so squeezing this volume would be like a can of soda. And right when you open that can of soda, air escapes out of the can. That's because it's under a lot of pressure. So this is considered high pressure. Low pressure, you could think of like a plunger. I mean, anything that's sucking a vacuum, anything that air is trying to come into that system, that would more likely be a low pressure system. That's a low P. Cool. You guys with me so far? Any questions on air density or air pressure? At any point during this talk, feel free to unmute your mic and let me know if you have a question. I won't see if you type in the chat box or if you, I think there's a hand raising button. I won't see that either. So just unmute and let me know if you've got a question for me. We'll get into it. Cool. So to start out here, kind of the basic concept that's going to really going to fuel every part of meteorology and wind and everything that we're talking about here is going to be this concept of circulation. If we look at the ground down here, and this is the world, so we have a sun. What the sun is doing is it's giving off radiation. There's three different ways that heat can move through matter. That heat can go through convection, which is when heat moves through a solid body. It can go through convection, which is where like you could have wind moving across something hot, and that wind is going to pull the heat away with it. That's convection. And finally, you've got radiation. And radiation is actually a type of light. It's kind of in the infrared spectrum, so we don't see it with our eyes, but you can pick it up with like a thermal camera. And that radiation is going to heat up anything that it hits that's at a lower temperature than it is. So in this case, the sun isn't really hitting the air because the air is transparent. So instead, the sun is moving through the air. The radiation from the sun is moving through the air, and it heats up the ground. Not the air, heats up the ground. And then I mentioned that convection. Kind of what that does is it takes some of the heat from the ground here, and it slowly heats up the air right above it. Then we have this hot ground kind of warming up the air. I mentioned it up here earlier that density is a function of temperature. And what we can look at now is that if the temperature is increasing, that leads to the density of that air decreasing. And anything that's dense is going to sink below anything that's less dense. Anything that's lower density is going to float, right? You can think of like a balloon of helium. Helium has a lower density, so it floats above the air. So in this case, now we have this warm air right above the ground. And so that warm air is going to try, here we go, is going to try to go up. So it's going to expand up and kind of away from the ground. Now as it does that, as it leaves, that would leave us with this area down below here where that air is kind of going away. It's rising up and leaving the ground. And we can't have a complete vacuum there, so instead, more air from the side comes in to fill its place. And this is usually cooler air that comes in to fill the place of that air that warmed up and rose away. That air is then going to get heated up by the ground, which is being heated by the sun, and it's going to rise. And that's that circulation process. After the air rises up sufficiently, it'll start to cool down in the higher atmosphere because it's no longer being heated by the ground, and it's expanding a little bit due to the lower pressure. And so it's cooling down. And so as it cools down, it's going to come back down and fill in the void that this air that's moving sideways created as it filled in. And so this right here, now we can really see this shape of this circulation that we're talking about. This is kind of what drives the motion of air across the Earth. This is why we see wind. This is why we see high and low pressure regions. It's all due to this uneven heating from the sun. All right. I've got a few more kind of like that density and pressure that we were talking about. Just a few more terms to kind of get into before we get into more weather systems. But before I do that, do you guys have questions on the circulation thing yet? All right, cool. And this whole circulation system, as I've drawn it here, is known as a heat low. Heat low because it's heating up the ground, and as it does so, it's creating a lower pressure area and lower density area, and so it's rising up. Cool, so heat low. All right, so next I'm going to talk a little bit about water vapor. I meant to do this before circulation, but here we go anyway. So that water vapor in the air, the main thing to consider when we look at how much water is in the air, how much humidity is in the air, those are the same thing, is that water is going to be less dense than the air. And that's gaseous water, water vapor. That's not liquid water. Liquid water is, of course, a bit denser. That's why it's not floating up above the air. So with that, if you have high humidity, that means that your air is less dense. So as the percent of water in the air goes up, the density goes down. Cool. So what that means is it's easier for humid air to kind of lift up as it gets heated. And so with that, if we have humid air rising up in one of these heat low systems, as that humid air gets higher and higher up, it's also cooling. It's also moving into a lower pressure area, and eventually it reaches a point where it's going to cool to form a cloud. Cools to form clouds. My spelling's atrocious, so I apologize about that. But what that means is that on top of any rising air mass, on top of a lot of rising air masses, we can expect to see some clouds. So a lot of pilots that are flying cross country, as they're going thermal to thermal, they'll recognize thermals across the flatland based on the clouds that are on the top of those thermals. We'll get into a bit more detail on that in a little bit. Cool. And then final thoughts here. We'll talk a little about air masses, and air masses are going to be coming up a lot during the rest of this talk. An air mass is kind of just an area, a large area of air. I mean, we're talking states in size, large area of air. It has roughly the same properties in terms of temperature, density, humidity, and pressure. And we usually distinguish between air masses simply as a warm air mass or a cold air mass. Yeah, and so these are also have a big effect they're also affected by the pressure. And one thing to think about is that in general with air masses, these warm air masses, right, they do have a higher temperature and they have then a lower pressure. Cold air masses tend to have colder temperatures, but higher pressures. Higher pressures. Cool. And then in between all these air masses, there are fronts. And a front we think about as kind of that dividing line between air masses. And I mean, the areas in between, it's not like a stark change that you would cross some line and suddenly hit the other air mass. I mean, these are transition that it's going to move from warm air mass to cold air mass, but we kind of define the middle line in between as the front. And so we think of it as a boundary between these air masses. You'll see these on pressure charts as these lines with different spikes or kind of bubbles. These are usually filled in. So here in this case, this is a cold front. This is a warm front, is how these will be labeled from here on out. And they're defined by what's following them. So in other words, if a cold air mass is coming in, that means that you're going to see a cold front hit one day, and then within the next couple days, you'll be in the middle of that cold air mass. Similarly, a warm front is going to come in before we hit a warm air mass. Or if we're looking at our pressure chart, right, our warm air mass is considered a low pressure area. So that warm front is going to be what leads your low pressure in your area, while the cold front is going to be what leads your high pressure system coming in. Cool. So with that, let's take a look at what these fronts actually look like from the ground level. So we've got our ground down here. Okay. And so we're standing here, standing on the ground, looking kind of sideways. This isn't a top-down, this is first-person view, kind of what's going on. So if our cold front is coming in, it's moving in this way, this is going to be cold air. We're actually going to see this kind of curved shape to how that air kind of rolls in. The reason for that is that as it's pushing in, it has momentum and it's moving to the right in this case. But it is heavier than the warm air out in front of it. So down low, that's going to look like kind of this rolling over as it's trying to push this warm air mass out. And higher up here, the warm air mass still wants to stay floating up above the cold air mass as long as it can. So that's why we see it curve back like this. Again, this is a cold front, so we're going to see these little spikes. This is just, the spikes are just symbology. There's no physical meaning for that. Cool. And so with this, we see our warm air out here, right? It's kind of getting pushed out here. But that also means that if it's getting pushed out, it's getting pushed up at some amount because there's air out in front of it. So we end up seeing a lot of this kind of vertical air motion right in front of your cold front. I should label this as my cold front. And that vertical air motion tends to turn into very large cumulus clouds. And so this is where we're going to start seeing like thunderstorms, overdeveloped clouds, that sort of thing. Meanwhile, after that front passes, you're more likely to see pretty clear skies with maybe some smaller puffy clouds. Cool. So in a cold front, that's usually when we see a lot of that overdevelopment in the clouds and a lot more instability in the air. Cool. And then now let's look instead at a warm front. Ground down there. The warm front comes in, warm air comes in, and it already wants to sit on top of that cold air that it's replacing. So as it's starting to push in, it's actually just going to kind of lay down at a pretty linear angle. Put our little symbology on there for a warm front. Now what this means as a pilot is we're going to look out here, and if everything's set up kind of just right and you're looking at it from the right angle, you'll actually see this kind of stratus cloud layer that follows this angle up in the sky. I think is pretty cool. Now down here we do still have a little bit of our cold air kind of circulating and moving around, so we might see a little bit of turbulence near the ground. Not really the point here though. The point here is as this warm air is coming in, this warm air is in a low pressure region. That low pressure means it's easier for that air to lift up. And so we're going to see these stratus clouds usually kind of following this line on the front and likely causing a larger stratus layer behind them. That might be like an overcast day type of a thing. Cool. You have questions on this so far? Anybody? All right. Now that we kind of know what these fronts look like, let's talk about the actual pressure systems themselves. So to do that, first we'll go over the Coriolis effect. Coriolis effect, something along those lines for spelling. So the whole idea behind the Coriolis effect is that the Earth's rotation rate is actually really affecting how things turn on the northern versus southern hemispheres. This is my attempt at drawing the world. We've got the equator is the solid black line, and then these dashed lines would be, if you were to walk straight from the North Pole to the South Pole, that's what these dashed lines would represent here. So our Earth is spinning right this way because the sun's rising over here in the east, setting in the west. And that means that inside of this area, we can see that this area right here on the equator is traveling at fairly long ways. Well, this area way up here near the North Pole isn't traveling as far in one given amount of time. Let's say that's like a 2-hour period. So what that means is that this lower section of the entire air mass is actually moving a little bit faster than the top. And so that means that there's going to be some amount of rotation moving along with that, because the lower part is trying to speed up while the upper part is trying to, well, in this case, not move to the right quite as fast. So this is kind of what the Coriolis effect really is. And we see it in our air masses. I've been told sniper shooters in the Army have to take this into account at times. It doesn't affect the way your toilet bowl flushes. Sorry, everybody. That's not true. But it does affect our air masses. So what does this mean for our high and low pressure systems? Well, in general, this rotation rate is going to follow what we call a right-hand rule. The basic idea there being that if you have your thumb and you point that in the direction that your air is moving, either up in a low pressure region or down toward the ground in a high pressure region, then your fingers wrap around in that direction of rotation. So in this case, let's say we have a low pressure region, air is more likely to be kind of lifting in this low pressure region because it's warmer air, it wants to rise. That's kind of what we talked about in our circulation heat low talk. So air is going up. We've got our little hand here, there's our thumb. And fingers are going to wrap around that direction, right? That means that our rotation rate is going to be going counterclockwise as it goes up. Similarly, but to the opposite effect, in a high pressure region, we're more likely to see air kind of getting pushed down toward the Earth. That's what's causing that high pressure, that force pushing all the air down. And so in that case, we're going to see a clockwise rotation as the air is kind of pushing itself down. Cool. So now let's look at our pressure systems. If we had, let's say, a low pressure region out here, maybe another one out here, high pressure, and another high. So in a pressure map, we're going to see what are called isobars, and that's basically a line along which the pressure is constant. A bar is a unit of measurement for air pressure. That's why it's called an isobar. So let's draw a few isobars in. And we'll talk about a little bit what they kind of mean. Isobars should not cross. So it's a lot like a topographical map here. We've got these high pressure points, and they're in the center of all these isobars. And low pressure points, also in the center of these low pressure region isobars. As we move away from the center of that high pressure region, we're seeing slightly less pressure on each line. And then as we go toward the low pressure region, that's when we get to the lowest pressure. So that's kind of what we're looking at here. These are these isobars. Then if we look at our right-hand rule again, in these high pressure regions, we've talked about that already. That high pressure is because that air is kind of being pushed down or pulled down, I guess, by gravity. Right? In those low pressure regions, there's less pressure because the air can kind of lift up a little bit easier. And so with that, we'll look at our right-hand rule. High pressure region, air is getting pushed down, in this case, into the page. This is kind of looking from space down onto Earth. Air is getting pushed down, which means that we have this clockwise rotation of the air along these isobars. Similarly, on the low pressure region, we now have thumb pointing up out of the page, fingers wrapping around counterclockwise. See this counterclockwise rotation. So this rotation, this is actually the winds that we're feeling. I know we hear a lot about like things go from high to low pressure, and that's true here as well. But that high to low pressure movement is movement of these pressure systems. This is looking at like movement of a large mass of air over maybe a state in the matter of a few days. So that's not going to be the type of winds that we're going to feel. Instead, we'll feel this rotation around these pressure systems. What that means for you is if you're planning a trip a really long ways out and you have some forecasting on what these pressure regions are going to be doing in that area, you can kind of see what the general trend for the winds should be. Right? If I'm planning to travel somewhere that's, say, located right here, I can expect just by looking at this map on this high pressure, we're moving into a high pressure day, that my wind direction, maybe not constantly, but in general, is going to be relatively from the north. Cool. And in between all these pressure systems, that's where these fronts come in again. So we've got a low pressure region here, so we're going to see this low front. And we've got high pressure right over here. That's going to be this high, or cold front. In between, we'll have occluded pressure regions, basically kind of combating high pressure regions together. There's a few other kind of unique pressure regions that, or unique fronts that I'm not going to get into right now. They're not usually wildly important, I don't think, especially as newer pilots. So now if we're going to look again at that high pressure region, then we're looking sideways again from the ground. High pressure. As I've been mentioning, we kind of have this force pushing the air down. So in general, most of the air is going to be pushed down and kind of away from the center of these high pressure regions. So what that means is that as we're kind of just gliding along out over a valley, we're not going to see a widespread amount of lift. If anything, we might notice that our glide isn't quite as good as on a low pressure day. But when we do hit a thermal, that means that thermal has enough energy and power to push up through all of this kind of air getting pushed down around it. And so we're likely to see really strong lift in these thermals. And those are usually topped by some cumulus clouds rather than like a stratus cloud. Cool. Now, on the other hand, we can look at a low pressure region from the side here again. In that low pressure, the pressure is low because the air is easily lifting up and away from the ground. So we're more likely to see this kind of widespread lift in our low pressure region. Well, maybe light lift, but definitely widespread. This doesn't mean that you're going to launch your paraglider on a low pressure day and just start going up forever. But it does mean you're more likely to find a higher number of these lighter thermals that are kind of moving up along with the low pressure airflow there. Probably should have drawn those in another color. You're likely to see more thermals, but maybe weaker or maybe weaker These are normally known as kind of fizzy days, is what a lot of paragliders are calling, because it feels like there's just these tiny little bubbles everywhere kind of picking you back up. This is where we're going to see more kind of widespread cloud layers, often some stratus cloud layers, things like that, because all that air is easily lifting, bringing humidity up with it, and eventually that humidity is condensing into a little cloud. Cool. You guys have questions on these pressure regions? No, we're moving into different types of clouds, and then more and more info from there. All right, we'll talk about clouds. I've already been alluding to this, but we have stratus clouds that we're more likely to see on low pressure days. And the main thing with these stratus clouds is they're going to be present when there's weak but widespread lift, meaning that kind of everything has a little bit of a tendency to just lightly rise up without too much power or strength. On the other hand, we'll have cumulus clouds, and these cumulus clouds tend to be that kind of cotton candy looking cloud, right? You can see a lot of cumulus clouds kind of standing off on their own. Sometimes you'll get a whole bunch of them together. But in any case, those cumulus clouds, they're usually topping off thermals, and so that's kind of the top of your usable lift on a thermal. You'll see them usually scattered toward the beginning of a high pressure region or shortly after a cold front comes through or during a cold front. And the big thing with cumulus clouds is these are what lead to overdevelopment and eventually OD for overdevelopment, and eventually they can lead to thunderstorms. A thunderstorm is essentially an overdeveloped cloud that continues to grow and grow and grow, and then lightning happens, which is bad. Well, bad for us up in the air, right? Now, if there's rain coming out of these, that's cumulonimbus. If not, we just call it a cumulus. Hopefully we aren't flying around cumulonimbus clouds. That would be a bummer. So a few other kind of fun or unique cloud types. One's called a lenticular. Some pilots out here call them lennies. They look like a contact lens from the side. Lenticular. And these are a really good indicator that you're looking at some really strong wind. These can stand alone up in the air, but more often you'll see what's called mountain lenticular, where they're literally going right over the peaks of mountains. You'll see this a lot at Big Sky if you're ever in that area on a super windy day. You see these standing mountain lenticular. Basically what it tells us as pilots is that wherever that is in the altitude, there's really strong winds there. So if it's low, definitely not a good day to fly. If it's high, probably also not a good day to fly, unless we're just on some really short sledders and the wind is calm down on the surface. Cool. A few other things to note. There's what's called Virga, which is basically rain that's falling out of a cumulus cloud, but it's evaporating before it hits the ground, and that'll usually look like this kind of striation coming off the bottom of a cumulus cloud. And if you see that, you can assume that a lot of the air in that cloud is kind of dumping down. So if it's on a small cloud and it's a long ways away, it might not be a huge concern for you. But if it's on a good-sized cloud near you or not, you can expect that all of this air that's rushing down, as it hits the ground, it's going to have to turn and rush away. So you might end up looking at some really big gust fronts if you're concerned about gust fronts based on the size of your valley. And then finally, another thing, I'm not quite sure how to draw this, but I'll do my best. We'll put a little top of the cloud there. Imagine here that this gray section down here is the bottom of the cloud that we're looking up at. So this next thing is called Mamatis, and it's kind of these hump shapes on the bottom surface of the cloud. And that's usually indicative that there's going to be rain happening soon. What that's telling you is that there's a lot of turbulence churning and kind of downwash coming out of this cloud that's pushing all these little bumps down. So that's another sign that it's probably not the right day to be out flying. If you're seeing that Mamatis cloud, you're more than likely going to see rain happen in the not too distant future with those coming in. Cool. Any other thoughts on clouds or any clouds I'm forgetting that I should be talking about here? Anybody? All right, then. In that case, let's look at some of our small scale or maybe site specific weather patterns. We'll look first at sea breeze and land breeze. Basic idea on the sea breeze is it's a lot like that circulation that we were talking about earlier, only it's really easy to see your kind of temperature gradient here, because as the sun's out there heating up the ground heats up pretty quickly, has a higher specific heat capacity than the water. So with that, that means the ground's going to heat up faster than the water, and so that air is more likely to heat up and rise. And as that air rises, we still have all this cool air over the ocean, and so that cooler air is going to swing in to take its place. And so that's why a lot of coastal sites have really consistent and really laminar wind. They don't have any obstructions out in front, but they do have this consistent pull of air from the land that's getting heated up, pulling in that sea breeze. Now, what's interesting on these, I think, is that this sea breeze can extend into the land as much as 30 miles. So you really just have to be kind of near a coast with a decent site without obstructions or mountains in the way to benefit from some of the sea breeze. They can get strong though. I mean, these can get up to 20 miles an hour, sometimes even more. And final thought here is like large lakes have the same effect. You can have kind of the sea breeze off of larger lakes like Canyon Ferry, Utah Lake, Salt Lake, anything like that. Now the other side of the sea breeze is going to be the land breeze. So that water heats up slower than the ground, but it does still heat up. What that means is at night, we'll draw a little moon up there to show that, yeah, that's totally a moon, and it's totally night. The water does heat up, and it holds heat longer than the ground. Water holds heat longer. So now we actually see that we have a bit more warmth, kind of residual warmth from the day in the ocean, which is going to lead to rising air over the ocean. And this ground is going to cool down a lot faster. And so we're actually going to see that cool air now over the ground falling back toward the ocean to take its place. You see this kind of flow in the morning and throughout the day, and then as it gets late into the evening, you see that flow come back out. Basically, what that means as a pilot is if you've been soaring on a coastal site and kind of you're nearing sunset and your wind is starting to die down on you, you can expect that in a fairly quick transition, you're going to see the winds reverse the other direction. It would be really a bummer to be getting pushed out into the ocean in that situation. So as you're getting closer to sunset, good idea to wrap up your flight, even if you're rocking a 3-mile strobe so you can fly a little bit longer. Yeah. So that's going to be great knowledge if we're out soaring on the coast or even doing cross country out on the coast. I mean, 30 miles inland, you could easily be hitting some terrain to go for those long distance flights. But a lot of us on this call are inland flyers, Montana and Utah. So let's talk a little bit about upslope and downslope winds, or antibiotic and katabatic. Antibiotic is going to be an upslope wind. Katabatic is going to be a downslope wind. More than just a brewery in Livingston. Cool. So our basic concepts on these anabatic and catabatic winds, I'll draw this as if we're sitting on top of the M here in Bozeman, or a pilot hanging out. The main idea with these is that as the sun comes out and starts warming up the ground, that air, again, is going to rise after it's been sufficiently heated. But air kind of tends to cling to whatever it's on. And so in this case, it's on this mountain slope, and as it clings onto it, it's going to travel up the slope until it reaches either a sharp change in terrain, such as a peak or a tree line, or a sharp change in temperature gradient, such as a pond, a river, something like that. So it's going to kind of follow the terrain a good bit until it reaches something like that, and then it'll release off. So that's why in Bozeman here, I mean, we almost never see a light southwest wind, which is what we would want for an ideal day at the M. But almost every day, not long after sunset, we see the anabatic wind set up. And what we're waiting for is that anabatic wind to kind of push, to have enough strength in it to push through whatever remaining catabatic wind is there, as well as not be pushed out by any meteorological wind. And when that happens, that's when we can take our flight. And I mean, that's most days in the morning shortly after sunrise, or shortly after the sun starts hitting the landing zone. That's when we're going to start seeing that light breeze trickle up the slope that we can easily launch in for a nice flight. Now I'll talk a little about these catabatics. And the basic idea with that is after the sun has set and there's no longer heating down low, a lot of this air starts to cool, and as it cools, it finally starts kind of draining back down the mountain to fill in the valley down below. The main thing to keep in mind with this is that the transition from your daily breeze and your anabatic flow into catabatic flow can happen in a matter of like 10 minutes. I've definitely been up on the M a number of times with other pilots where, like, yeah, one person might be able to launch, but right after that, it's too late. Now that tailwind's starting to set in from the catabatic, everyone else has to hike down. So moral of the story, if you're going to hike up for an evening sled flight, just know that if you start feeling that flow coming down the mountain, it's probably not a fluke thing, and it's probably not going to go away. So it might be an indicator that it's time to hike back down instead of go for that flight. And even as you're setting up, if you're hoping to get the final flight right at sunset, if you're heading up there and getting clear on all your lines, you're clipped in, you're about ready to launch, always, always, always just do a common sense check. Again, is the wind hitting my face? If it's hitting the back of my neck, I'm not going to be able to launch. Cool. You guys have any questions on anabatic, catabatic wind? All right. Not quite sure why I have this right here in my notes, but I do, and so I'll talk about it now. One other thing just to consider, Matt, I know we've been talking about this a little bit, but if you're on launch and let's say you're about halfway up, you didn't go up to the peak, and you feel that headwind, you might think, oh, it's all great, it's time to launch. If you hadn't done your homework, you don't know the forecast, and you didn't hike up to the peak, the big risk that you might be seeing here is you could actually have wind coming from the backside of the mountain, actually coming up over and rotating in to where you're launching. Now with that, I mean, you do have a headwind right on launch, right? So technically, it's not going to feel difficult to pick up that wing, move forward, and get off the ground. When it's going to get bad is once you've reached just beyond this point as the pilot. This is you on your wing up here. Once you reach just beyond this kind of upslope little breeze, because now we're in this really turbulent region of air where all that air is kind of churning and pushing mostly down. So what that's going to mean for you is that you're more likely to see some frontal collapses, if not full collapses, and just a lot of sink. And you're going to be draining right down to the landing zone, hopefully still making your landing zone with enough glide. and with enough active piloting to keep your wing open. So, I mean, this is one of the biggest things that can really hurt new pilots, is not considering that they could be in a area of rotor. And so I just always like to add this into most of my talks, is keep this in mind. If you are just, if it just looks like a nice day out and you go hike up your hillside to go launch, even if you're standing on launch, it's worth double checking that all the wind in the area is doing what you think, including that wind aloft is forecasted for kind of what you're feeling. Because if you see wind indicators on the other side of the mountain here going the other way, that's a good sign that you're in a dangerous rotary spot. Cool. Let's see, up next here, I'm going to talk a little bit about thermals, and then about turbulence, and then about different types of lift. I believe that's all I'm covering for the rest of the night. Do you guys have any questions before I move on? Feel free to chime in. All right, so we've already talked a little bit about what this thermal lift is. At least I've been talking about them as I explain other things. But really, this thermal is kind of a vigorous, localized, heated area that's causing this column of rising air. So as this air heats up, let's say we've got this really hot region down here. As that air heats up, it finally starts to rise and climb, and it moves up, and air around it sucks in toward it as it's moving up when it's down near the ground. And then somewhere higher up, that's when we start to see these little cumulus clouds kind of topping out the usable lift. So what are these thermals? How do they behave? What do they look like? We can kind of expect that wherever we see this thermal trigger, as it's starting out in the day, there's going to be kind of a bubble that releases and climbs up, and then it'll be calm for a while, and then another bubble of hot air that finally kind of releases and climbs up, and then it'll be calm for a while. And as the day progresses, those bubbles get closer together until eventually you do end up getting this you do end up seeing this nice rising column of air that's a lot more uniform as it's moving up. But the downside of that is at this point in the day, now we're also seeing that as that air is moving up, it's kind of churning what's around it. You can think of flow moving around an obstacle in a river. So that churning is going to be happening out here, and that's going to be turbulence. So as we enter a thermal, you tend to have a little bit of a bumpy ride right as you get into one of these thermals. And then once you're in it, you're usually in a more laminar flow as long as you stay inside. But that's also a good indicator if you're thermaling to what is the edge of that thermal. Well, if I'm coming around what I think is one side of the thermal and my wingtip has a little deflation or a little collapse, that's usually a good indicator that you're grazing the outside of the thermal, and it could be worth tightening that turn in a little bit more. Cool. Now, when these get scarier, is these thermals, they'll like keep rising and climbing, and usually they'll build a little cumulus cloud up on top. But what gets scarier is when that cumulus cloud actually overdevelops and turns into a thundercloud. That overdevelopment is going to look like a cumulus cloud. It's basically taller than it is wide. Taller than it is wide. That's what's going to lead into a thunderstorm or a rainstorm. And the reason that this happens, because as I mentioned, these thermals, they tend to have a cloud that's kind of the top of that lifting air. But as water condenses from a gas into a liquid, it actually releases heat. So, in other words, you've got a beer koozie, right, for your beer to keep it, well, as most of us think, to keep it cold because it's like an insulator. The other thing it's doing is it's keeping condensation from forming on the outside of that can, because that condensation is the same thing as what we're talking about here. It's humidity that turns into liquid water, and as it does that, it releases a little bit of heat. And so that's actually going to heat up that beer inside the koozie faster, and so that's why you use the koozie to stop that. So same thing in our cloud here. As this humidity goes from gas into liquid water in here, a little bit of heat's released. So let's do one of these. Do that. Cool. So as our gas turns into a nice liquid droplet of water, it actually releases out a little bit of heat in all directions. And as we already have been talking about, that hot air is going to rise, and so that means that we're going to see more rise going up. And as more air is rising, the last little bits of humidity are condensing more, and that's what's building this cloud into this towering, scary object up above your heads. Also means as a pilot, this is a dangerous place to be, right? If we're up near this cloud and all this condensation's happening and this heat's getting released and air is rising, we wouldn't want to be up in here because we're going to stay in a lot of really strong lift inside of that cloud, right? And we won't be able to see. So a lot of kind of scary things here. But let's take a closer look at that cloud itself and talk a little bit about how it's behaving. If we have all this condensation and we have rising air, just like in these thermals, that means around the outside, we have some amount of kind of rotation, right? It means we have mechanical turbulence. And down below here, if this cloud is still climbing up, that means that air has to fill in. And so that air is going to fill in from the sides of the cloud and wrap in here. So this is where you really get stuck in this thing we call cloud suck. Because as a pilot, if you're right here trying to fly out this way, you're now fighting a headwind of this wrapping turbulent air that's kind of refeeding the cloud. So in general, again, this is kind of a general rule. We don't want to get within this kind of cone that has like 45-degree angles with the edge of the cloud there. As long as we're outside of this, it should be easier for us to fly away. So basically, as you're thermaling up, if you're getting close to that cloud, it would pay to kind of get out of this cone and not get into the cone in the first place, because that's where you're going to see the most likely cloud suck situation. Hopefully I don't have to go into too much detail here, but getting stuck in a cloud is bad for a lot of reasons, mostly being the severe downdrafts and gusts that'll happen inside of that cloud, as well as all the water that's inside there is going to get on your wing. Your wing's going to get wet and it's not going to fly correctly. It's going to be really turbulent and it's going to be hard to get out of. To top it all off, you won't be able to see hardly a thing. So moral of the story there is probably just take it easy on flying up near cloud base, especially on days where conditions seem strong. Well, do you have questions on these thermals? I'm not really trying to go into how to fly thermals, more just
one quick question, John, or Ryan. So you talked about when you see your wingtip start to collapse, you can assess that you're kind of getting toward the edge of the thermal, right? So how do you get out of the thermal?
Yeah, so this kind of turbulence on the sides here, sides of these thermals, I mean, it's there and it's going to feel bumpy as you fly through it. It may even cause some small collapses, but it's kind of the cost of entry into thermaling, as you're more than likely going to be flying through some of these little turbulent regions to get into the thermals and flying through them to get out. Now, conveniently for us, here I drew this thermal happening in absolutely no wind, but more than likely, if we're out flying, there's going to be some amount of wind. So let's say there's some base wind, in this case flying from left to right here. It means that this thermal is going to climb and it's going to get pushed sideways. Now our thermal's kind of off at this angle, and that's why, Matt, if you saw that video I posted on the WhatsApp there, that's why you saw John and my flight track was kind of not going straight up. It was going kind of sideways in these circles. That was kind of our flight path. So the nice thing about all this, though, is that turbulence doesn't have a ton of strength to it, which means it can be pushed around. And so when we have wind coming in and pushing our thermal off to one side, it's also pushing all of that turbulent region off and around to the back of the thermal. So as a pilot, that means that the downwind side of a thermal is probably going to be even a little bit more turbulent, but the windward side and either side that's not up or downwind are likely to see a lot less of this turbulence. So when you're going on these cross-country flights, if you're really starting to figure out where your thermal triggers are and you can start visualizing where you expect these thermals to be, it pays to enter the thermal and exit the thermal from the sides rather than from behind. Because if you enter from behind, that's when you're going straight into this turbulence, which is not fun. While entering from the sides and going into the thermal that way, you're kind of avoiding that whole turbulent region to begin with. Yeah. And just another thing, Matt, not having any airtime yet, and certainly not having any active airtime yet, we'll get you out in some conditions where things are just a little bit bumpier, so you can kind of feel what this is like. And in like light turbulence, you notice it, but it doesn't have to be a terrifying thing. It's just a little bit shakier, like some slight turbulence on an airplane. Not necessarily always going to be a deal breaker for your flight. And the other thing, I was talking about that kind of idea where you have that turbulence on the side and it can kind of tell you where the side of the thermal is. So try to draw this thermal a bit wider. Just reminds me of a flight I had up in Canada last summer, where I was this little pilot in here doing my thing, circling around and around and around. It came up like this. And then I remembered coming around kind of the leeward side of this thermal. And as I did, my wing just started to kind of graze this turbulent area back here. And as it did, this wingtip, it actually did take a little collapse. It kind of looked like a big ear kind of forming on that side. And it did that, and then it opened back up. So instead of panicking or leaving that thermal, it just told me, well, that means I'm not riding the core, I'm riding the outside of this thermal. So I just tightened my turn up. As I tightened it up, I had much stronger climb rates because then I was right in the core of that thermal where the climb's the strongest, rather than floating around on the outside of it. That's where you can get a lot of communication kind of out of this little bit of turbulence and this little bit of bumpiness in the sky. I remember my first trip down to Mexico to fly. What was her name? CS. She described flying through the turbulence and flying in bumps as playful bumps telling you where to fly. That didn't make me feel any better at the time, but certainly does now. Cool. Does that answer some of those questions, I hope, Matt? And does anyone have any questions?
Yeah, thank you. I mean, that kind of cleared it up for me.
Great. All right, we're going to talk a little bit about, a little bit more, I guess, about turbulence and different types of turbulence. So the main, let's say the strongest and most easy to see kind of turbulence is just mechanical turbulence known as rotor. We'll call it mechanical rotor. Sure. And basically, all that is air flowing around any solid object. As it does so, there's going to be an area behind it that has this swirling air. And that's that turbulence, is this swirling, churning air. And you can picture this as like flow in a river moving around a rock. And those little eddies that form and release, those are like our turbulence here that we're talking about. So here I just showed, like, let's say we have air coming over a building. You've got this region behind it that's going to be in some turbulence. So in this particular case here, if we were kiting, we wouldn't want to be kiting right up behind the building here. That's where we'd be in a lot of turbulent air anyways. But more likely what we'll see is that turbulence turning into rotor on a mountain. And so that kind of rotor, I mean, we're talking it goes up and swirls and can, depending on the wind strength, can be a large, fairly large area behind the mountain range. This is why we're never flying on this leeward side, certainly not telling new pilots to fly on a leeward side. As pilots, we want to be out here on the windward side of these mountains, where that airflow is laminar and smooth. Cool. So another type of turbulence, it's called shear turbulence. Basically, so shearing is when you can think of like sandpaper on wood. That's kind of a shear force. It's friction. It's sliding across a surface. That's kind of what that shear means. And so shear turbulence is if we have airflow in one direction up high and airflow in another direction below that, or even just at a different speed below that. And in between there, you're going to see air wanting to move this way. We're going to see air wanting to move this way. Air wanting to move. And eventually these have to join back up. So here's some circulation starting. And so this is where we're going to see some amount of turbulence in between here. There's a shear layer. If you're hear the pilots talking about, oh, there's a shear layer at this height, you know what that means, that as a pilot, once you get up into this height, that's where we're going to start seeing a lot of bumpy air that if you want to continue to try to fly through it, there are certainly times when that does work out and you can climb up above it and then the air is laminar again up on top. If you don't want to deal with that, it just means that you kind of have a ceiling on your altitude on how high you want to fly, and you can stay down here in the more laminar airflow. Now, what I think is interesting about this is these swirls actually can do some pretty cool things if there's a cloud in that layer. Let's say again, we've got airflow going one way here and going the other way up top. Our cloud, which today is purple, which would be reason for concern, if not for being just a theory here. So, as this cloud's forming, it can be really interesting to see these. They're called what's called Kelvin Helmholtz instability. It kind of is this wave breaking shaped cloud. All I can tell you is look for this because it's an extremely distinct shape. Once you see it, you'll know that, like, oh, that's what Ryan was talking about. They're pretty cool, and I mean, they're just caused by that rotor that's kind of forming in between these two layers. It's just pulling parts of the cloud up and then cresting it over. I think they're really interesting, and it's just one of the very few ways that the sky actually tells us what's going on with the air. Cool. Final thing I have is on aircraft vortices. We talked about that quite a bit in my aerodynamics talk. That's kind of that induced drag, right? Let's say this is our paraglider. Line's coming down here. Somebody down there. So aircraft vortices, there's two kinds that we might deal with here. I'm going to copy this so I can use it again. The first is going to be from our wingtip vortice. And that's this rotating air that's caused because we have low pressure up here on top of our glider, high pressure underneath, which causes lift. And so the air wants to wrap around from high to low pressure. And as it does that, it gets some rotation amount to it and it starts kind of falling out the back. So you have this on both sides in opposite directions. So what this tells you basically is don't fly directly behind somebody when you're up close to each other. That's when you're going to start seeing effects from this. I encourage a lot of you, if you have friends, to go out and go do some kiting with, to play with this wingtip vortice and to play with wake behind your wing. Because if you have somebody up in front of you, you can bring that wing up right up close behind them as long as you're in safe conditions. And you might see that collapse happen as your wing is coming in and taking some wax from this kind of turbulent rotation out the back of the wing. Now the other form of this aircraft turbulence, well, let me do it. There we go. Is if you really pull these brakes in the back down, now you've got this big flap out the back. It's with that air that's coming into your wing has to get pushed down and then out the back, and then it's swirling as it exits from behind your wing. Basic idea there, to be a courteous pilot to the new pilots around you. If you notice that there are students out in the air and you're sharing a ridge, let's say at point of the mountain together, as you're passing in front of that other pilot, it's common courtesy to let those brakes out quite a bit so you aren't causing as much of this wake. That way they aren't hit with this weird little mechanical turbulence. What it also tells you as new pilots is that when you're passing somebody on a ridge, if you're on that kind of downwind side of them, you might get hit by that wake, and especially notice what they're doing with their hands, because if they're deep in their brakes, you're definitely going to feel that wake. And so it's going to be kind of bumpy. It's going to jostle you around. And so you'll want to have some active piloting control to just help keep your wing inflated. Cool. You guys have questions on this turbulence? I talked quite a bit about that thermal turbulence already, so we won't go into that again. But next I'm going to be talking about lift. Cool. So enough of those scary parts of flying. We'll talk about lift, the fun part. So first, we'll talk about Ridgelift. I've been alluding to Ridgelift a bit. Basic idea with Ridgelift, if we look at a cross-section of a mountain from the side, let's say, as wind approaches it, it has to either go to the sides or go straight up. And if there's a lot more mountain range on either side, that means it's going to be going up. And so as pilots, we can now launch from here. Now we can go back and forth in this rising air. Now this kind of topography I've drawn is pretty similar to point of the mountain. So at the point of the mountain here, we'll also see this kind of bench effect. The idea being that you can actually climb up decently high on this front little bench in this rising air. And once you're high enough that your glide ratio will keep you in lift when you get to the back, now you can go back and forth along this ridge and fly up to the higher bench. And that kind of bench idea is fairly common and something you'll see at other sites as well. But ridge lift, what I like about it is it's usually pretty laminar airflow. You're dealing with air that's coming from a long ways off with nothing in front of it and just hitting a range and going straight up. With that, there's a lot of right-of-way rules, right, that we have to follow if we're in ridge lift, because usually places that have good ridge lift have a fair amount of pilot traffic. But one last consideration here is that there can be turbulence in this air. And so as a pilot sitting on the ground down here on launch, one thing to do to gauge what that air is actually doing is to watch those pilots who have launched before you if you're in a popular site and see what they're doing with their hands. If you notice they're making a lot of kind of twitchy motions, that usually means that they're having to do a lot of active piloting to combat some of that little deflation that's going on due to the turbulence. So rather than just watching their wing, see what they're doing with their hands, see if they're moving around a lot with their weight shift. Those are going to be good indicators of how much work they have to do just to keep their wing inflated in the air. Cool. I talked about thermals a fair bit. Different right-of-way rules in thermals than there are in ridge lift. So if you're going to go out in thermal, just make sure you brush up on those first. But I won't go into more detail on that right now. So the next one is going to be convergence lift. Convergence is basically you have two kind of air masses that are flowing straight at each other. Once they hit each other, they have nowhere else to go but up. Now, these convergence areas can be really cool because they might not be super wide this way, but they could go on for miles and miles and miles, kind of along that convergence line. What's tricky about them, though, is if there usually isn't perfectly laminar flow here. So if you do have any gusty conditions, that means that the strength on either side here is going to change, which that's going to shift your rising convergence line. So it might not be totally consistent, and it might change just throughout the day. So when you're riding on a convergence line, if you're on a good heading, stick with it. But once you find yourself kind of losing that lift, it's time to turn left or right to try to find it again, because you're probably dropping out one side of the convergence. For example, you might be following this line here and everything's going great until suddenly you've left that convergence line, so you'd have to make a hard turn to get back into it. Now these can be really turbulent down low near the ground here, because this is where this air is kind of hitting each other and really mixing. So convergence lines are usually the nicest if we've already gotten up fairly high, either from ridgelift, thermal lift, or just a higher launch, and then we're kind of flying into them from higher up. Cool. Got another form of lift here called wave. Depending on where you're at, you definitely, some places mountain wave sets up, and some places it's way too strong when it does. But the basic idea is on a really stable air day, meaning that if you were to lift air up, it would want to come back to where it was rather than continue floating away. So on a really stable air day, as some ridge lift forms on the front side of a mountain, as it comes back, it's going to drop back down a little bit too low and then rise back up to try to meet its same spot, and do that for a few cycles back and forth. What we're looking at here is that there are some regions in here, and I'll highlight them in yellow, that they still have that vertical air motion. You've got air that's moving up into the sky. So as pilots, it is possible, under the right conditions, to fly in that mountain wave. That being said, right in these areas behind the mountain wave, we're likely to see some pretty severe rotor, as well as off the back of the mountain there. But you'll also see some really interesting shaped clouds in these areas that tend to be like, kind of look like a cumulus cloud, but almost like hot dog style, really long. They're going to extend kind of in these stripes. So I encourage you guys to get on and Google some mountain wave photos. A lot of airline pilots will be flying way above them and take really cool photos of just stripes of clouds along the sky. And like I said, it's sometimes possible to fly in that lift, but a lot of places where this mountain wave situation happens, it only happens in really strong winds. Now in Missoula, they tend to see it a fair bit, and so you actually see these striped clouds once in a while. But that's usually when the wind is way too strong to be flying. So I'm trying to remember, I read recently in one of these books about people flying the mountain wave, and it's a possibility. I think it's a unlikely thing, but just something to kind of keep in your tool belt, I suppose. Cool. And yeah, so my final form of lift that I want to talk about is called glass off. Basic idea on glass off is if you have a valley, usually in like a higher pressure day. Oh man. Usually in your higher pressure day, as the sun's moving through the air, it's heating up the valley floor. Right? And so that valley floor is storing all this thermal energy. But as the sun's continuing to move across the sky, eventually it gets far enough over that one side of that valley is inevitably going to be under some shade, right? Hopefully that's the west side of the valley, otherwise something might be terribly wrong. But when that shade starts setting in on the west side of the valley, that air is going to cool and it's going to sink. That's that Katabatic flow, which is going to set in on this side of the valley, but it won't set in quite yet all the way over here where the sun's still heating up that face and all this air in between. So what the sinking air wants to do is it wants to stay low. And so it's going to roll down under all the air on the valley floor and just start layering on top and filling it in. As it does that, you get this really slow lift in the air that's just all over the valley. But it might be really strong over here on the east side because where all this air has been kind of flowing down and pushing all these almost thermals out onto the other face. So it can be really tricky to launch during glass-off conditions, sometimes impossible. But if you're already up in the air, these glass-off conditions, I mean, it's usually like you don't feel lift at all, but you're out there flying and you have like a perfect glide ratio. You just don't lose any height, tool around for the last 30 to 45 minutes of your flight. It's known as magic air because it does just feel magical. It's usually very smooth, very laminar. Feels like boating on a glassed off lake. That's why they call it glass off. Cool. Well, do you guys have any questions on any forms of lift here? This is actually going to wrap up my meteorology talk. This is just kind of the fundamentals for your introduction. There's so much more to learn. I'm learning more and more every single day, just reading a lot of different books on paragliding. And so that's what I would encourage all of you to do is just keep being a student of the sport. Once you really get some of your mechanics down and some of your in-air skills down, the sport just completely comes down to being your own micrometeorologist. And your sole concern is thinking about, okay, what's the terrain look like and what does that mean it's going to do to the wind and how big is that cloud and is it growing or shrinking, is it too big, just on and on. Really I just want to preach that meteorology is where it's at, and the more you know and the better you get at your meteorology, the better flights you'll have.